All right, guys, so the last couple of days, we've been talking about density, and we talked about how close the particles are together. So that was kind of the first step. So particles that are closer together are going to be more dense. So right now, we're all fairly spread out. So we're not very dense. But say I cut the volume in half, and I make you guys all kind of come back together. Now we have more mass in a smaller volume, which makes it more dense, okay? So we initially talked about density equals mass divided by volume. So my units are grams per milliliter. So as I'm solving for density, I want to make sure I'm in grams for mass, milliliters for volume, or I could also have it in centimeters cubed. So if it's centimeters cubed, you're getting centimeters cubed because you do the length times the width times the height. If you have an irregular shaped object, what did we do last week?
Water displacement?
Yeah, we had that water displacement. So we took the object, put it in water, submerged it, and saw how much that volume changed. However much it increased by, that is my volume, so I'd be solving for volume there, and then I could get my density. Remember, density is a characteristic property. So if I have a sample of aluminum, and I take that aluminum and then I cut it in half, did my density change? Nope, density did not change, right? Now, we also talked about relationships. We said density is mass over volume. If I make the mass greater, so there's more students in here, more or less dense? More dense. If I increase my volume, now we get to spread out even more. What happens to density? Less dense. Think all the way back to the gizmo. What happens with temperature? How can I make something more dense with temperature? Colder, right? Make it colder. So colder, particles come closer together. So usually the solid is going to be the most dense phase for whatever type of substance you have. Except who? Who's the weird one?
Water.
Water, right? Water is actually the densest at that 4 degrees Celsius, which means as a liquid, that's where we see the densest for H2O. Once you go below 0, then we obviously are getting into ice, the solid form of water, and that's going to actually float. The density is less than 1, okay? All right, now the second thing we talked about, we did particle spacing, we did calculations, we did temperature, we did mass-volume relationships. The very last thing we're doing is the graphical view of density, okay? So when you guys first look at a graph, so look at this graph that I have right here, and I want you guys to tell me what are some things that you notice in that graph. Yeah, what do you got?
Well, there's the volume on the x-axis, the mass on the y-axis, and we have 3 lines for different substances.
Perfect. All right, so y-axis has mass, x-axis has volume. There's 3 different lines. They're not all on the exact same line, so that means they all have different what? Densities, because they have different slopes. So remember, when we are solving for slope, do you remember back in math class, what did you guys do to get slope? Oh, that's our equation. That's a linear expression. You're right, though. Y equals mx plus b. M would be the slope. Rise over run. Okay, so as I'm looking at this, I can calculate my slopes by figuring out the rise over the run for each one. Well, this is my rise is the mass divided by the run, which is volume. Mass divided by volume is what? Density. So if I said solve for the density of a substance using this graph, really all I'm asking you to do is figure out its slope, right? All right, so number 1, it says, what does the slope of the line represent? Well, then it represents density. All right, so looking at our 3 lines, who has the greatest slope? Let me scroll back in so you can see it again. Who has the greatest slope? Salt water, right? So greater the slope. Another way I could have said that was if it's steeper, okay, steeper the slope, it has the greater density. Perfect. Could I solve for density too? Okay, so we want to try to find a place where it crosses the line nicely. Do you see anywhere where it crosses nicely for the dotted line? Oh, not really. But what about right here? What is the rise and then the run for that point right there?
Rise 55.
All right. What would be the run?
50.
Okay. Everybody got a calculator?
I do.
All right, 55 divided by 50 should be 1.05? 1.1. Boop. Let me see. 1.1. All right, so does that make sense? Should it be greater than 1? Yeah, right? Because we have water up there, so we know that this slope better be greater than 1 because the line's above, it's slightly above the water. So we know that the slope, the density has to be greater than 1, okay? Which means then if I was going to solve for the slope for, let's say, the bottom one, our alcohol, let's take a look. It kind of crosses here, don't you think? All right, so come across, what is the rise? And what is the run?
You did the runway run this way, right?
All right. Sorry, rise, run, you're right. Rise, beeps, runs. All right, 60 divided by 70 gives me what?
0.8 or 0.9.
If you round it, 0.9 grams per milliliter. Does that make sense that it should be less than 1? Yeah, definitely. All right, so as I look at that, if I was to, say, create a beaker, if I had a beaker, which liquid would be on the bottom?
Salt water.
Yes, because that's the most dense. Which would be on the top because it's the least dense? The alcohol. And then regular H2O would be in the middle. Okay? Even if you shook it up, shook, it would separate back out because they have different densities. It wouldn't form a nice homogeneous mixture. Okay? They would actually separate out a little bit more. Okay? 1.1. Did we flippy floppy? Oh, you're right. That's 0.9. I did the one for salt water. You're right. All right, let's take a look at the next one. So we got the calculations of the density. We did our rise of our run on the other one. So that call was good. All right, so what if instead I changed the question for you? What if I said, what is the mass of the alcohol? If you want, we could use our triangle. If I use that triangle, remember I cover up the M, and then what is my equation? Yeah. So the volume, we're trying to figure out what is the mass of alcohol if I have a volume of 70. All right, so we're actually going to go back. Do you remember what the density of? All right, so what's 1.1 times 70?
No, it was like
It was 0.9.
Oops. All right, 0.9. You're right. All right, what's 0.9 times 70 then? What'd you get? Oh. Doing it in your head?
63.
All right, we got 63. What would be my units for mass? Grams. Booms. Look at that. 63 grams is what we'd be looking for. Now, you guys want to see a faster way to do that? What? There's always a faster way. Come on, dude. Always a faster way. All right, so it said, what is the mass of alcohol that has a volume of 70? Well, if I go back to my graph, find volume of 70, come up to the alcohol, and then look. Come all the way across. And I can estimate mass over here. So you could do it that way as well. Okay? That one's going to be a little less precise because we're kind of eyeballing it. Where does it fall? There's not a million tick marks on that y-axis, but that would be another way that we could do this. So what would be the volume of water if it has a mass of 40? Well, let's just go to the graph. If it has a mass of 40, Come across to find the water, which is right there. Come down, and what's our volume? 40. Now, you're probably like, well, hey, that one's easier because I know that the density is 1. So if I do mass divided by density, 40 divided by 1 is still going to give me 40. So whether you choose to utilize the graph or whether you want to actually do the calculation, both are going to get you the answer pretty fast. Okay, so it's not too big of a deal if you want to do the math, but if you want to go to the graph and you think, hey, I can eyeball it and estimate it from there, that's also another great option for it. All right, so if I wanted to add another one with a density of 9.92, where would this go? Remember, this one was 1.1, this is 1.0, and this one's 0.9. Where would my line go?
What's the density really?
The other density is 0.92.
Right above.
Right above the alcohol, right? So I'd start at 0. See if I can make that a nice straight line. Explain everything doesn't have the same nice straight line features. Man. All right, let's see if I can make it nicer.
Do you allow a margin for error when it comes to like estimating because it's not like specifically written on the graph?
Yeah, so you could estimate. Now, could I also say, hey, if it was something easier, like you guys will have a question on the worksheet today that has you draw a line for a density of 0.4. Well, to get a density of 0.4, I just need a rise 4, run how much? 10. Rise 4, run 10. So on that one, it's a lot easier to graph. So depending upon what it is, the main thing is I'm trying to get you to understand the placement. So because it's 0.92, it needs to go between those two. So I wouldn't be looking for a specific point on the graph. I would be looking to make sure that your line is between those two. Does that make sense? So it doesn't have to be perfect, but at least has to be in the correct location. So again, if I was to place all of them in the different beakers, so if I go here, and again, here is my unknown right there in the middle, green. Who's the most dense again? Then, well, our green line, right? That's our unknown. And then the alcohol. Okay? So again, density is a characteristic property. It helps us identify substances no matter how much of that substance we actually have. Okay?